Jai Hind dear students, I am Dr. Preeti Mittal and today we are going to start magnetic effects of electric current. It's a very small chapter but an interesting one. Do you know the working of fans, electric motors that is there in mixer grinders, washing machines, apart from that generation of electricity at the power stations? This is all based on magnetic effects of electric current. But how it was discovered to us, that was came to be known accidentally. Isn't that interesting? Once Hans Christian Ørsted was doing some experiments in his laboratory and there was a magnetic compass lying on his table. So what is a magnetic compass? A magnetic compass consists of a freely moving needle, and this needle will point in the direction wherever the Earth's north pole is there. The head is going to point towards the Earth's north pole, and the tail part is going to show Earth's south pole. Now, if any other magnet is brought close to it, then the like poles of the magnets repel each other, and so if you bring the north pole of any magnet, this north pole will be repelled by it. Okay, so it's like a freely moving magnet only. It's just in a compass, so it's free to rotate, and it's just like any other magnet. The like poles are going to repel each other and the unlike poles are going to attract each other, and when it is not surrounded by any other magnet, the head is going to point towards the Earth's north pole. So a magnetic compass was lying on his table and he was carrying out some experiments. So when he joined the circuit, he found that there was a deflection in the magnetic compass. It was very much surprising for him because though there was no other magnet nearby. Then he turned off the current and found that the compass again came back to its neutral position. Then he again turned on the current and found that again the deflection was there. And he concluded that there is a magnetic field generated. Whenever current is flowing through a circuit, then a magnetic field is generated around it. And that's how we came to know about this magnetic field. So we are going to see about the properties of this magnetic fields as well as the magnetic field lines around the bar magnet. Okay. So first, continuing with this only, the properties of the magnetic field. Whenever there is a current carrying conductor, then that can produce a deflection in the compass. That means a magnetic field is generated near the compass, near the current carrying wire. Now, how this magnetic field is going to change? Is it having any particular direction? Yes. These magnetic field lines always have a particular direction. How Ørsted came to know about it? Ørsted came to know about it by just reversing the circuit. Earlier, whatever circuit was there, he just tried to reverse the circuit and was surprised to find that the compass was now pointing in the opposite direction. That is how we came to know that these magnetic field lines have a peculiar direction as well. Now, what about the deflection in the compass? Is it going to vary with the current? So let's see. If we have a current carrying conductor in which current is flowing, then here current is flowing, the deflection produced in the compass will vary with the amount of current flowing through the circuit. Means more the current through the circuit, more will be the deflection produced in the compass. Means more will be the current, stronger will be the magnetic field. Okay, strong magnetic field will be there, then the compass needle will be showing more deflection. Now, second thing is the distance. That is true for any magnet. If you are having a magnet, just imagine this current carrying conductor as another magnet. So what will be there? If you bring another magnet, then near the magnetic field is more. And as you go away from that magnet, the magnetic field is going to decrease. Similarly, here also, if you have a current carrying conductor, the distance is inversely proportional to the magnetic field. So if the magnetic field we talk about, then it is inversely proportional to distance from the wire. So if we increase the distance from the wire, if we go away from the wire, then the magnetic field is going to decrease. But if we come near the near the current carrying conductor, then the magnetic field is also going to increase. Okay, so more the current, stronger will be the magnetic field, and more the distance, lesser will be the magnetic field. Fine, I hope this is clear. This deflection is showing the magnetic field. So more the current, more will be the magnetic field strength at that point. Okay, both these things are about the current carrying conductor. Now just let us see about the properties of magnetic field lines around a bar magnet. Okay, so if we have a bar magnet, it will be having two poles, north pole and south pole. If we try to draw the magnetic field lines in this using a compass, then we get that the magnetic field lines are like this, They are in the form of concentric circles arising from the North Pole and going towards the South Pole. Here I draw one more magnetic field line. They are all arising from the North Pole and going towards the South Pole. Similarly, magnetic field lines needs to be drawn below this also. So at every place, they are arising from the North Pole and heading towards the South Pole. Now, in your exam, for 2 marks, you could be asked to write the properties of magnetic field lines. So what are the properties of these magnetic field lines? These magnetic field lines always starts from the North Pole and end up at the South Pole outside the magnet. But inside the magnet, they are from south to north. So outside, it's north to south, and inside, it's south to north. The second property is that these magnetic field lines never intersect each other. This is very important as an individual question also, that why these magnetic field lines never intersect each other. These magnetic field lines never intersect each other because suppose if they intersect with each other, suppose I draw another magnetic field lines and they intersect each other. So at this point, if I place my compass, that compass should point in 2 different directions because we have drawn these magnetic field lines using a compass only. So if I place my compass at this point of intersection, my compass should point in 2 different directions, and that is not possible. So we say that these magnetic field lines never intersect with each other because if they intersect with each other, then our magnetic compass at that particular point will be pointing in 2 different directions, which is not possible. Okay. Next, these magnetic field lines are always in the form of concentric circles. They are always in the form of concentric circles, one after the other. They are complete circles are there. And the fourth point is that the degree of closeness of magnetic field lines shows the magnetic field strength. So near the poles, if we draw the magnetic field lines, we will find that near the poles, these magnetic field lines are very close to each other. But as we go far away from the magnet, they are very distant, having a great distance between 2 magnetic field lines. So the degree of closeness of the magnetic field lines is directly proportional to the magnetic field strength. If they are closer to each other, that means at that place, the magnetic field strength is also more. Okay. So this question comes as a 2 marks question. What are the properties of magnetic field lines? We have discussed that. Okay. I told you that if we have a current carrying conductor, there is a magnetic field around it, and that magnetic field is having a particular direction. How can we come to know the direction of the magnetic field line around a current carrying conductor? We can do it by using right hand thumb rule. Okay, just our right hand and we'll know the direction of the magnetic field. So suppose this is a current carrying conductor. In this, the current is moving in the upward direction towards north. So what will be the direction of magnetic field? That we can come to know by using our right hand thumb. So suppose we hold this current carrying conductor. Suppose this is the current carrying conductor and the direction of the point of the tip of the pen is in the direction of current. And I hold it in such a way that my thumb points in the direction of current, then the curl of my fingers, the turn of my fingers, the way my fingers are turning, that will show the direction of the magnetic field. Okay, so this is how the magnetic field could be shown. And if I draw these magnetic field lines, so this is the current carrying conductor, the magnetic field lines are going in this direction. This is the direction of the magnetic field lines. When the current is going upwards, the turn of the fingers is like this. So the direction of magnetic field lines is anti-clockwise. You can see that it is anti-clockwise. Why I'm saying anti-clockwise? If it is a 12 o'clock position and this is a 6 o'clock position, your clock moves like this: 1, 2, 3, 4, 5, and then 6. But here it's moving in the opposite way, so we call it as its anti-clockwise direction. Okay. Suppose the direction of current is downwards. Then what will be the direction of magnetic field lines? It will be in that direction because the turn of my fingers are pointing in that particular direction. So the magnetic field lines will be in the clockwise direction. That will be in the clockwise direction. The current is pointing in the downward direction. Then the direction of magnetic field lines will be in the clockwise direction. Okay. One question is also based on this direction of magnetic field lines. It's given in your NCERT book as well, that the current is flowing from east to west. From east to west, current is flowing. What is the direction of magnetic field lines at a point just above and just below this wire? Okay, so the current is flowing from east to west, so I have to point my thumb in this direction. Now if I draw the magnetic field lines and if I observe it from the west direction, they appear to be, just do it along with me, then you will be able to understand it in a better way. Then you can see that the direction of the magnetic field lines is anti-clockwise when observed from the west. Okay, so suppose this is west and this is east. So you can see if I observe that my fingers are turning anti-clockwise. So the direction of magnetic field lines is also anti-clockwise when observed from the west direction. But now if you observe from the east direction, you can see that my fingers are turning in the clockwise direction. So when observed from the east direction, then the magnetic field line is showing the direction in the clockwise direction. Fine? So when observed from east, it is clockwise. When observed from west, it is appearing to be anti-clockwise. Just try it with your own hand, then you will be able to understand it in a better way. Okay. Now, next, instead of taking a straight wire, if we have a circular wire, then what will be the direction of the magnetic field lines? Let's have a look with that. So if we have a circular loop and we connect it to the two terminals of a battery or a cell, then the current will arise from the positive terminal and will be going towards the negative terminal. So if we observe the direction of magnetic field lines across this part, the current is moving upwards. So the direction of magnetic field lines will be anti-clockwise and the direction of magnetic field will be somewhat like this. If I draw one more magnetic field line around it, then the direction of magnetic field lines will be all in the same direction, that is anti-clockwise direction. If on that side I try to observe the direction of magnetic field line, what will be there? The current is pointing in the downward direction. So the direction of magnetic field line will be pointing outwards, means it will be in the clockwise direction. This is one magnetic field line that I have drawn. This is the second one I have drawn. I hope this much is clear to you. Now consider real concept, real important thing, that is if I draw some more magnetic field line, if I draw one more magnetic field line, let's see about it on both the directions. I'm drawing one more magnetic field line. Then you can observe that all the magnetic field lines at the middle point, at the center of this circular loop, they are all pointing in the same direction. So inside the circular loop, all these magnetic field lines are going to be added up, because from this side also the magnetic field lines are moving in the upward direction, and from this side also they are moving in the same direction. So when they are going in the same direction, they are going to just get added up. Because of the two sides of the wire, the magnetic field lines inside the circular loop is going to increase. This will even increase more if we increase the number of turns. If instead of taking just one turn of the coil, if I just don't end my wire here, if I just take some more turns of my wire, this is one more turn I have taken, then the magnetic field lines due to this wire will also be in the same direction, because the direction of current is the same. So if we increase the number of turns of this circular wire, then also the magnetic field strength inside the wire is going to increase. And this is the principle that is behind the working of a solenoid. On the principle of this only, that the magnetic field lines are going to be added up when they are in a circular loop, then the total current is going to get increased, the total amount of magnetic field is going to be increased. This is the principle of working of a solenoid. So what is a solenoid? In a solenoid, we take a cylindrical insulated structure and we wound copper wire, insulated copper wire around it. We are having so many turns of the copper wire, and so you can make it out that if the turns are so many, then the magnetic field because of those wires will all be getting added up. Okay, I hope that is clear. So now this solenoid will also be having the magnetic field lines around it. This solenoid is going to behave like a bar magnet. And for learning about the properties of solenoid only, in the starting of the chapter, we have discussed the properties of magnetic field lines around a bar magnet. Let's see how it goes. So the magnetic field lines around the solenoid also will be moving from north to south outside the magnet and south to north inside the magnet. So they will be moving in a particular direction, and the direction from where they are coming out, that becomes the north pole of the solenoid, and the direction from where they are entering into the solenoid, that becomes the south pole of the solenoid. So it's like this. So in this case of solenoid, in case of this solenoid, you can say this part of the solenoid is the north pole and this part of the solenoid is the south pole, because all the magnetic field lines are coming out from the north pole and entering into the south pole. The direction of magnetic field lines, whether it is a bar magnet or a solenoid, the direction of magnetic field lines are always north to south outside the solenoid or outside the bar magnet, and inside they are from south to north. Okay, it got erased. South to north inside the solenoid. So now what is very, very important is one experiment that you must have done in your childhood. If you take a magnet with you and you bring some pieces of some nail, okay, you must have seen some all pins, है ना? And if you bring a magnet close to an all pin, what happens that if suppose this is a all pin and this is a magnet, this all pin will get stuck to it. Okay, now if I have another all pin and if I bring this all pin next to this all pin, what happens? ये भी उससे चिपक जाती है. You must have observed that. So is it a magnet? Is this all pin a magnet? No. But in presence of this magnet, this all pin has gained a magnetic property, due to which another all pin will be getting stuck to the first all pin. ये एक मैग्नेट नहीं है, फिर भी एक मैग्नेट के कांटेक्ट में आने से this all pin of mine is getting behaving like a magnet, and due to which another all pin is getting stuck to it. So now what happens? A piece of iron, if it comes in a magnetic field, then this also gets magnetized. But as soon as you remove the magnet from the all pin, now this all pin is not going to behave like a magnet and it will not be stucking any other all pin. Any other all pin will not get stuck to it. Okay. So what is there? Why I am talking about this childhood experience of yours? Because this solenoid also will be helping us to get a temporary magnet. If we place a soft iron inside this, soft iron is and a piece of iron. So if we place a piece of iron inside this solenoid, since it is placed in the magnetic field, that piece of iron will be behaving like a magnet. But it will be behaving like a magnet as long as this magnetic field is there. And this magnetic field is there as long as the current is there in the circuit. As soon as you turn on the circuit, that current will be flowing in the circuit. Due to that current, magnetic field will be generated. And if we place a soft iron inside the solenoid, it will be behaving like a temporary magnet. But if we turn off the current, then what will happen? If we turn off the current, no current is flowing in the circuit, then no magnetic field will be there and the iron piece will no longer be behaving like a magnet. Such a piece of soft iron which behaves like a magnet only in presence of this magnetic field, such a magnet is known as an electromagnet. Means it was behaving like a magnet in presence of electric current only. And such a magnet is known as electromagnet. Electromagnets are very important. It's there in our daily life. It is there in all electric motors like washing machine, mixer grinders, fans, electric fans. So they are all using electromagnets. Okay. Apart from that, one more application of electromagnet is an MRI machine. MRI is magnetic resonance imaging. We'll talk about it. So that machine is also having an electromagnet for its working. Okay. These electromagnets are very powerful magnets, even powerful than a permanent magnet. Okay. And they could easily lose their magnetic properties as soon as you turn off the current. So if you want that your magnet should behave like a magnet for a particular duration of time only, and when you don't want it to behave like a magnet, it shouldn't be behaving like a magnet, then you should use a electromagnet. Okay. So I hope that much is clear. What is important for your exams from is that what is a solenoid and what is an electromagnet. Properties of magnetic field lines, or draw a figure showing the magnetic field lines around a solenoid. So that you can all write. Okay. I just told you about MRI. So let's discuss about MRI. What is MRI? MRI is the magnetic resonance imaging. In our body, the impulses in the nervous system are traveling in the form of electrical impulses. And we know that whenever electric current is there, a magnetic field is generated around it. So we can find out the imaging of our organs could be done by using this electric current of our body and visualizing the magnetic field around these organs. So that imaging technique to visualize the organs of the body is known as magnetic resonance imaging, or MRI. Two organs of our body that have a very strong magnetic field and so their imaging could be done very well is your brain and the heart. They are richly supplied by nerves and so they have a very good magnetic field around them, and their imaging could be very accurately done using an MRI. Okay, so that is about MRI. Now, second last concept of the chapter is about force on a current carrying conductor placed in a magnetic field. Now, what is that? Let's talk about it. Suppose we have suppose this is a current carrying conductor and this is a magnetic field. So this current carrying conductor is having its own magnetic field, because we already seen it that whenever we have a current carrying wire, that is having its own magnetic field. And now if we bring a magnet close to it, there will be either attraction or repulsion between the two. They are either going to attract each other or they are going to repel each other. The direction of this force of attraction or repulsion could be known by using our left hand now. Earlier we used the right hand to find out the right hand thumb rule. Now it's a turn of our left hand and we stretch out the fingers of our left hand in such a way that they are all perpendicular to each other, and we use the rule Fleming's left hand rule. Okay. The application of this left hand rule is very interesting. What sort of questions can come in exams based on this left hand rule? That I'm telling you. So suppose we have a current carrying conductor and that is placed in a magnetic field, and we want to know that what will be the direction of force. That could be known by using the Fleming's left hand rule. This is the Fleming's left hand rule. Okay. So now what is this rule saying? Suppose we stretch out the fingers of the left hand in such a way that they are all perpendicular to each other. Now one common mistake the students do is that they sometimes turn this like that. Okay. Don't take it like this. This index finger should be pointing outwards only. So it should be forming an L between your index finger and your thumb. Don't do it like this. Okay. Do it like this only. So there is a L formed between the index finger and the thumb. These two are perpendicular to each other. Then these two are also perpendicular to each other. Okay. So this is how you need to stretch your fingers. Now what could be the pattern of questions? We'll directly move to that. Suppose we have a beam of protons that is going towards the east. Towards the east, a beam of protons is moving and a magnetic field is acting on them. You all know that magnetic field is always from north to south. So in this case, if the magnetic field is acting in such a way that it is towards the north, in this plane, I have kept the magnet in such a way that the direction of magnetic field is towards the north, then what will be the direction of force on these protons? So let's find it out. So if the direction of protons is towards the east, that means the direction of current is towards the east. Why I'm saying so? Because the direction of protons and the current is the same only. Whatever is the direction of positive charges, the same is the direction of current. The direction of protons is towards the east. Direction of magnetic field is towards the north. So this finger of mine, the index finger of mine, shows the magnetic field. The middle finger of mine points in the direction of current. Then the thumb points in the direction of force. My thumb points in the direction of force. So the protons are moving towards east. The magnetic field is towards the north. So you can see that the thumb is pointing outwards. Okay. Or if you draw in your copy, you will be finding that your thumb is pointing in the upward direction. So you can write the direction of force as outwards or upwards. Both are correct. Okay. But what will be the direction of force if this is not the direction of protons, but this is the direction of movement of electrons? Suppose we are given that a beam of electrons is moving towards the east and a magnetic field is acting towards the north. What is the direction of force on them? Let's find it out. So whatever is the direction of flow of electrons, the direction of current is always opposite to that. Okay. Remember in electricity chapter, the first video that I have uploaded, I told you that earlier it was believed that the protons are moving in a circuit. So direction of flow of current is from positive to negative, but actually the electrons are moving. I have not made a complete circuit. I have not added any resistor or something. Okay, but you can take that. The direction of electrons are actually flowing, and the direction of flow of electrons is opposite to that of direction of flow of current. Okay, that we have discussed in the first video of electricity chapter. If you haven't seen that, just go through that. So the direction of electrons is given towards the east, means the direction of current will be towards the west. That is the opposite direction. Now it was given that the magnetic field is acting towards the north. So where is my thumb pointing now? It's inward. Or if you're doing in your copy, then it is downwards. So the direction of force in that case will be downwards or inwards. Okay. So such questions could be there in your exam. One such question is given in your NCERT book also. Try to work it out. Okay. So that was there. Now the last topic from the chapter, that is about the domestic electric circuits. Okay. In domestic electric circuits, I'm directly coming to the type of questions that you could be having in your exams. So in domestic electric circuits, we have appliances that are usually having either 5 ampere rating or 15 ampere rating. Two types of circuits are usually there in household circuits. The less power consuming appliances like tube light and all, they work at 5 ampere rating circuit, And the more power consuming circuits like electric geysers, washing machine, they all work at a 15 ampere power circuits. Okay. So that two types of circuits are there in your household circuits. Now, there we have in our household circuit, we have three types of wire. One is a red insulated wire, and that is called the live wire. We have a red insulation over the wire, and that wire is known as a live wire. Second is a black insulated wire, a wire having an insulation of black color, and that is the neutral wire. These two wires are going to pass through our electric mains. But we have a third type of wire that doesn't passes out through this electric mains and goes directly to the appliances, and the color code of this wire is green wire, and that is known as an earth wire. This green wire coated wire is known as earth wire. Okay, this earth wire is a protective device in our household circuit. How it is going to protect us? Let's say that. So this live wire and neutral wire, they are at a very high potential difference. In India, the potential difference between the two is kept to be 220 volts. In India, the difference in potential between the live and the neutral wire is kept at 220 volts. So what is happening is that the neutral wire is almost at zero potential, and the live wire is at approximately 220 volt supply. Now, when the current is supplied to different appliances through these wires, then the current will be flowing through them, and every appliance will be having a potential difference of 220 volt. In a household circuit, as we discussed earlier also, we are having all the appliances that are connected in parallel to each other, so that individual appliances could be turned on or off. If we would have connected them in series, then we would have to keep one of the appliances turned on, we have to keep all the appliances turned on only. Okay, so that we can just turn on and off any of the appliances of our choice. We have all the appliances in our household circuits in parallel combination. Now, what is the use of this earth wire? This earth wire is directly connected to the metallic body of appliances. Suppose this is my microwave oven, then the metal body around it is directly connected to the earth wire. So if there is any leak of the current on the metallic body, then what will be there? The current through the metallic body will be directly going to the earth wire, and passing through the earth wire, this earth wire is connected to the earth. That is why it is called earth wire. One end of the earth wire is directly connected deep under the earth on a metallic plate. When your house is constructed, at that time only a metallic plate is placed to which the earth wire is connected. So through the metallic body, if there is any leak in the current, then the current, whatever extra flow of current is there on the metallic body, that goes to the earth. And the earth is having very low potential, so all the current, whatever is there, that will be going into the ground, and we call it as earthing. Okay, so if you touch any appliance at your home and you are getting a shock, then just check your earthing. That might be damaged because of some reasons, and that would be leading to shock when touching any appliances. Okay, so this is the three types of wire. Just remember out of that, earlier we discussed about one of the things, that was fuse. Working of fuse we have discussed in the video of electricity chapter. So fuse and earthing wire, these are the two precautionary measures that are there in our household circuits. These are the two safety devices which are there in our household circuits. What are the two? Earthing, earth wire, or fuse. These two both provide us as a safety device. Okay, now we have two more topics left from this chapter, that is short circuiting and overloading. First is short circuiting. You all know that this live wire and neutral wire are having a very high potential difference. So if live wire and neutral wire accidentally come in contact with each other, if this is a live wire and this is a neutral wire, and if the insulation over them is damaged somewhere, and if they directly come in contact with each other, then the current from the live wire will be passing directly. And since a lot of potential differences between them, there is no appliance in their pathway, so a lot of current from the live wire will be going into the neutral wire, and this is known as short circuiting. This is known as short circuiting. This short circuiting could be really dangerous because that could lead to a lot of heat generated in these wires, because a high amount of current is passing through the circuit, and that could lead to catching of fire at this place. Okay, that could lead to burning of wires and catching of fires because of this electric circuits. Okay, so whenever there is direct contact between the live wire and neutral wire, because of faulty wiring, this condition is known as short circuiting, and it could be really dangerous. Second thing is overloading. What is overloading and what are the causes of overloading? Short circuiting has just one reason, that is direct contact of live and neutral wire. Faulty wiring is the cause. But overloading could be due to three reasons. The first reason of overloading could be short circuiting. What is overloading? Whenever extra flow of current is there through the wire, that condition is known as overloading. So whenever excess of current is flowing through any circuit, that is known as overloading. So one cause of overloading is this: when the live wire and neutral wire come in direct contact with each other, a lot of current will be flowing through that circuit, and that is known as overloading. Second cause of overloading could be potential hike. Sometimes in your household circuit there is voltage fluctuation, and if there is a hike in the potential, that could also lead to overloading. So if excess of current is flowing in the circuit, that is the second reason of overloading. Now, the third cause of overloading. Suppose we have electric mains. Suppose you have a power socket, and in that power socket, if you attach many appliances in just one socket, that socket can bear a maximum of 15 ampere current. And suppose you are connecting too many appliances to that. Suppose you are connecting two appliances that are each demanding a power supply of 15 ampere each. Then that will be too much for that circuit, and that will be one of the causes for overloading. Okay, so if there is too many appliances that are connected to a single socket, that is the third reason for overloading. How could you prevent this overloading? You need to check your wiring. That should be proper, that shouldn't be damaged. Second way to prevent overloading is to check that you are not connecting too many appliances to a single socket. If the single socket is there, so the total number of appliances that should be connected should not exceed the limit of 15 ampere current. It should not be consuming more than 15 ampere current altogether. Okay, so too many appliances should not be connected to a single socket. That is another way of preventing overloading. Okay, one more numerical check question is given in the NCERT book, that if you have an electric socket, suppose you have an electric iron, okay, and that can allow a maximum of 5 ampere current through it. That can allow a maximum of 5 ampere current through it, and you connect an appliances through that is having a power rating of something, and that is connected to a potential difference of 220 volts. Okay, suppose the power rating is 100 watt. Okay, so in this case, what will be there? How much current will be flowing to the circuit? P equals to VI. So if the power is 100 watt, potential difference is 220. How much current will be flowing to the circuit? Circuit will be 100 upon 220. So it's 10 upon 22. So it's less, it's less than 1. Okay, so there is no problem in this. It's 10 upon 20, so 22, it's a 0.9 ampere current is flowing to the circuit. So it's fine. But if you connect a 1000 watt or if you connect a 2200 watt appliance to that circuit, now what will be the problem? So here we have. So now, how much current is flowing to the circuit? 10 ampere. But how much it can allow you is just 5 ampere. So the total current flowing the circuit exceeds its maximum limit. And in that case, what will be there? The fuse wire is going to melt away. Your appliance will be still saved, don't worry, but the fuse wire is going to melt because excess of current is flowing to that circuit. Okay, so this is a similar question is given. The values are different. A similar question is given in the NCERT book. You can just work it out. So that's all from this chapter, magnetic effect of electric current. We have tried to revise everything in just one video. Okay, so keep studying and score well. Have a nice day.